Hello everyone, thanks for coming my presentation. My name is Zihan Chen. I'm a second-year master student in National University of Defense Technology. Today I'm going to present our paper, Imperceptible Adversarial Attack via Invertible Neural Networks. And this work is under supervision of Professor Wentao Zhao and Junjie Huang. You are able to read the full paper and access the official code from scanning the following QR code. Many works have proven that deep neural networks are vulnerable to adversarial examples and can misclassify the adversarial examples to an erroneous class label. For example, when we add mild perturbations on the clean image, the classification will change from dog to ostrich. Adding adversarial perturbations to the clean image is a predominant way to generate adversarial examples in recent works. Traditional methods like PGD mainly utilize the gradient skewness, but add perceptible modifications on the clean image. But dropping discriminant information of the original class named addDrop has also proven to be able to successfully craft adversarial examples, which provides a new perspective. addDrop learned the quantization table in the JPEG compression framework, leading to dropping information in the frequency domain. From the above analysis, we roughly categorize the adversarial examples generations into ending and dropping information. The adversarial attacks method based on ending information has higher flexibility in targeted or untargeted attacks, and method based on dropping information is more robust to denoising-based defense and has higher imperceptibility. However, their limitations are also obvious. Method based on ending informations add perceptible noise patterns on the clean image and has noticeable increase of image size. And method based on dropping information show limited performance on targeted attacks due to the decreased information. Because of the splitting process, there are some blocking artifacts on the generated adversarial examples by addDrop. Imperceptibility is an important criteria for adversarial attacks. However, it is not well attained by many well-known adversarial attack methods. From the following examples, the modifications added on the clean images are perceptible for human beings. Recently, there are an increasing number of works aiming to improve the imperceptibility of adversarial perturbations. Zhao proposed a perceptual color distance constraint leading to improved visual imperceptibility, and Luo proposed a semantic similarity attack and introduced a new constraint on low-frequency subbands, which encouraged to add distortion on the high-frequency areas. Inspired by the advantages of traditional ways and the limitations, we wonder whether it is possible to craft imperceptible and robust adversarial examples by simultaneously ending and dropping information in a unified framework. So the idea is find a network to learn a nonlinear transform with information preservation property to interchange information between the clean image and the target image. And the invertible neural networks are the suitable choice. Invertible neural networks are bijective function approximator due to their mathematical induced network architecture. Given an intermediate feature, INNs are able to perfect reconstruct features of other layers. That is, the information of INN's input is preserved throughout all its layers, and there is no extra information injected or lost. The overview of our method is shown below. The invertible information exchange module nonlinearly exchanges information between the input benign image and the target image. The reconstruction loss is utilized to constrain the optimized adversarial examples being close to the input clean image. The quantization module is set to run the pixel values of the generated adversarial examples to be integers and within the range from 0 to 255. The adversarial loss evaluates this similarity of prediction logics and the target label. And the target image learning module is used to update the learnable target image. Our proposed method consists of two main modules. The one is the Invertible Information Exchange module, which is set to generate an adversarial example by dropping discriminate information of the original class while adding adversarial details from the target image. And the second one is the Target Image Learning module, which is set to select or learning the target image as the source information for ending adversarial perturbations. We consider three approaches for selecting the target image, including highest confidence target image, universal adversarial perturbations as target image, and the classifier-guided target image. The detail of Invertible Information Exchange module is displayed in this picture, consisting of discrete wavelet transform, inverse discrete wavelet transforms, and multiple affine coupling layers. Discrete wavelet transform is used to disentangle the input image and the target image into low-frequency and high-frequency components, which facilitate modifications to the input image applied on high-frequency components, and therefore results in less perceptible adversarial examples. An inverse discrete wavelet transform has been applied to reconstruct the features back to the image domain. In the experiments, our recommended affine coupling layers is 2, and due to the information preservation property, the amount information of two inputs is the same as outputs, so the relationship between inputs and outputs can be represented as the two equations. In detail, sigma donates the dropped existing information for the clean image, and delta donates the added discriminate information from the target image to the clean image. The selection of target image directly affects the convergence speed of the network, so it plays an important role in our method. We propose three selection methods to choose the target image. Firstly, we select the image with highest confidence in each class, but the convergence speed is limited by the considerable amount of information unrelated to the target class. To overcome this, we generate targeted universal adversarial perturbations and regard them as a target image which only contains the information related to the target class and optimized in a data-free manner. But the perturbations need to be prepared firstly. Meanwhile, the success rate cannot reach 100% at end. To address these problems and accelerate the convergence speed, we make the target image to be learnable. Algorithm 2 means showing the detailed process. The target image is initialized with 0.5 and updated with the gradient from the attacking classifier. In this way, adaptively generated target images can embed more discriminate information of the target class, assisting the generation of adversarial examples. 6 comparison methods has been included for evaluation, with 3 well-known adversarial attack methods and 3 recent state-of-the-art methods. For fair comparison, all comparison methods perform targeted attacks with the least likely objective to avoid choosing closely related classes, which is less meaningful in the real applications. For the target classifier, we use pre-trained ResNet 50, and the adversarial budget is set to 8/255 with respect to L infinity norm. Except that the evaluation metrics are including L2 norm, which measures the average energy of the adversarial perturbations, L infinity norm, which evaluates the maximum perturbations intensity. SSIM accesses the structure similarity between two images, and the other two metrics both measure the perceptual similarity. And we follow add drop to select 2 common defense methods based on image transformation, JPEG compression, and bit rate reduction. And we also select purification-based method, neural representation purifier. The table 1 shows the accuracy and evaluation metrics on different methods on ImageNet 1K. And we can see that our method generated less perceptible adversarial examples with 100 attacking success rate. The corresponding visualizations are shown in this page. We enlarge the difference image 40 times for better perception. We can observe that our results are more imperceptible on both smooth region and edge region. For detailed visual comparisons, please refer to our website and paper. We have evaluated the performance of all comparison methods on the testing set of CIFAR 10 and CIFAR 100, which can also support that our method generates more imperceptible examples than other methods. And we repeatedly observe that our proposed method makes minor modifications on these two CIFAR datasets. Adversarial defenses aim to correct the prediction of the classifier and output the benign label. And robustness reflects the effect of adversarial attacks. The success rate is higher the more robust of the adversarial attacks. As for the testing the robustness of adversarial examples generated by add-in, we choose two transform-based methods, JPEG compression and deep depth reduction, and one purified-based method, NRP. When FID score is in the range from 2 to 16, add-in outperforms all comparison methods against JPEG compression and outperforms most comparison methods against bit depth reduction and NRP except SSAH. In conclusion, with the same FID constraints, add-in can generate more robust adversarial examples, and with the same attacking success rate, add-in can achieve a lower visual perceptibility. Our method also improves the interpretability of the generated adversarial examples. In detail, each line represents the three selections of target images. The clean image, the target image, and the generated adversarial examples are shown from row 1 to 3. The classification is changed from goldfish to face powder. In row 4, we visualize the residual information dropped by the networks to further interpret the results. The absolute difference between clean image and target image and the estimated drop information are shown in row 5 and 6. We observe that all methods drop in certain key features according to head, chest, and tail of the goldfish, and discriminate information of face powder. The difference image and drop information of add-in CGT are enlarged 150 times for better perception, which only makes tiny modifications on clean image and drops the boundary details of goldfish. The proposed method is tested on the other two adversarial budget constraints, and the adversarial examples are crafted successfully even under stricter constrictions. We also set experiments on different classifiers. When fooling a more robust classifier, add-in success in generating more imperceptible adversarial examples and guarantees 100% attacking success rate. In conclusion, we propose an adversarial attack via invertible neural networks, which generates imperceptible and robust adversarial examples by simultaneously adding and dropping information in a unified framework, and fully utilize the information preservation property of INNs. Finally, we improve the interpretability of adversarial examples. That's all for our work. Thanks for your listening, and if you have any questions, please feel free to contact us.